Hi students, welcome to lesson 92. I want to introduce you to a topic that is very important for every algebra student to conquer. This is a style of story problem called boat in the river problems. They freak people out, they mess people up, but I want to give you a pep talk in the beginning to assure you that the process isn't hard. We can break this down and make it really simple. But when you read the story problems, they always freak people out. They freak me out every time I read them over again. So stay calm, trust me, and let's talk for just a minute about this scenario. Imagine you're traveling in a boat. It could be a sailboat, a rowboat, a canoe, a kayak, a speedboat, a hydroplane, a yacht, whatever you want. Imagine yourself in that boat right now, traveling on a river. If you think about it, there are two speeds that are determining your overall trip speed. Number one is the speed of the boat. Whether it's sailing, rowing, motoring, whatever, your boat is traveling under some form of power, and there's a speed associated with that. The second thing that is happening is that if you're on a river or an ocean, let's imagine we're on a river because that's how these problems make the most sense, boat in the river problems, then the water has a speed, right? Because rivers flow almost all the time. They're not, the assumption we're making is that the water is not standing still, our boat is not standing still. So there's a speed associated with both of those things. And in order to use our usual rate times time equals distance formulas, which are going to be the backbone of these problems, we have to take into account that our rate is going to include both the speed of the boat and the speed of the water. All right? Complicated enough. Now, keep in mind that when you're going downstream in a river, when you're flowing with the current, your speed, the speed of the water will be faster than if you're going the speed of your travel will be faster than if you're going against the water, right? Okay, so that makes this complicated, but we're going to use some formulas here to keep it easy. If you're going downstream in your boat, you're traveling with the current, then your downstream rate is going to be equal to the speed of the boat, which we just identified as B, plus the speed of the water. Right? You're going downstream, you're traveling with the current, so your boat is zooming along and the water is zooming along in the same direction and you're being swept along at a very nice speed. However, if you are going upstream, if you're trying to travel against the current, then you've got a slightly different arrangement. You've got the speed of your boat, but instead of the speed of the water working with it, it's working against it. All right? Commit that to memory. Make sure that makes logical sense to you, that if you're traveling downstream, your boat is flowing with the water, the two speeds will be added together because they're working together. If you're going upstream, then the water is going against the speed of your boat. Make sure that's logical to you before you go on. All right, if we want to take these two special rate calculations and blend them into our usual rate times time equals distance problem, then it's going to look like this. When we're going downstream in our boats, our formula will look like this. Instead of just using rate, we'll use the rate of the boat plus the rate of the water times the time to equal the distance. And I'm going to subscript those. The time to go downstream equals the distance to go downstream. When we're traveling upstream, you can probably figure this out. It's the speed of the boat minus the speed of the water times the time upstream will equal the distance upstream. These are the final tools that we will use in order to do these problems. This is what needs to make sense in your brain. Once this makes sense, you can substitute it into our basic equation, and that's what leads us to these. So memorize, write them down in important places so that you will always have those in your brain, I promise you'll see them again in your career. So let's take a look at example 92.1 and see how we might apply these in a story problem. The words blow my mind. They'll probably blow your mind too if you're at all like me. Don't let it get to you. We're going to pick this apart. Robert and Clay could go 60 miles downstream in the same time it took them to go 20 miles upstream. If the speed of their boat was 8 miles per hour in still water, what was the speed of the current and what were their times? Ah! Okay, here's the strategy, you guys. To start out, what I like to do is make a list of my 6 variables. Speed of the boat, speed of the water, time downstream, time upstream, distance downstream, and distance upstream. There are 6 variables in this equation. I just listed them out. Now I'm going to go back through the problem and pick out what I need. Robert and Clay could go 60 miles downstream. So downstream distance is 60 miles. In the same time, it took them to go 20 miles upstream. Okay, so there's my distance upstream. My times are the same, so what I'm going to do is use T for both of them so that I don't have the subscripts. If the speed of their boat was 8 miles an hour in still water, okay, so that's the speed of the boat, then what was the speed of the current? That's the water. And what were their times? Okay, so we're solving for W and T, which makes sense. We can solve for 2 variables because we're going to have 2 equations. So I'm going to get a fresh piece of paper. I'm going to rip this one off so we can refer to it if we need to. We're going to start by stating our downstream and upstream equations. The boat plus the water times the time upstream equals the distance upstream, and then the other one is boat minus water. Oops, I put the wrong ones. Sorry. You'll have to catch me on these if I mess up. Time upstream minus equals the distance upstream, okay? The U, the upstream, is associated with the minus. The D, downstream, is associated with the plus. That's how I try to keep it in my head. All right, so now what we're going to do is use our chart of variables to just plug into our equations. So here I've got my list. Okay, 8 plus W, I'm substituting in. Time downstream, we're just using a plain T, equals the distance downstream is 60. Boat minus water, 8 minus W, times the time upstream, we're just using T, equals the distance upstream, 20. Okay, simple substitution. We check to make sure that we have 2 variables to be solved by our 2 equations. We're golden. So far, so good. All right, so now we're substituting in. Now, you guys, that's all that's new for us. We now can simply proceed to solve these equations in using the methods that we've been using for a long time. So let's just take a look. It looks like we need to distribute our T across this. So let's start by doing that in both cases. All right, so I'm going to have 8T plus, I'll write TW alphabetically, equals 60. And 8T minus TW equals 20. All right, so now we have 2 equations that are distributed, and we need to solve them as a system, right? We want to find a solution for T and W that satisfy both. So now we turn to our methods of solving a system of equations. We can use substitution or we can use elimination. My brain looks right here and sees the 2 plus and minus TW, and I think, oh, cute. I'm going to rewrite this over. You don't have to go through this much trouble. 8T plus TW equals 60. Forgot the 0. Okay, so I'm going to put that one on top, and then we're going to put this one underneath. 8T minus TW equals 20. And then I'm simply going to combine them in elimination. 16T equals 80. Divide both sides by 16. T equals 5. Okay, so the time that it takes these boats to make these trips is 5 hours. And we know that the times for both trips were the same, so we don't have to solve separately for downstream and upstream. The other part of the problem, the questions the problem asked were, what was the speed of the current and what were their times? So now what we need to do is substitute this back into one of our original equations, this one or this one, in order to solve for the other variable, which is the speed of the water. You could use either one. I'm going to go with this one because I would rather have a plus sign than a minus sign. So I'm going to take this 8 plus W in parentheses, 5 on the outside of that, equals 60. Yeah, so I'm just substituting in, and that's a 5, not an S. And now I'll multiply. 40 plus 5 times the speed of the water equals 60. Subtract 40 from both sides. 5 times the speed of the water equals 20. Divide both sides by 5, and I get that the speed of the water equals 4 miles per hour. It is a good idea to go back to your answers, check them for reasonableness, and attach a unit. Oh, wait, sorry, I attached the wrong unit. You guys must laugh so much when I make these little mistakes, because you probably catch them right away. Rachel, I can feel you laughing at me right this minute. Okay, so those are boat in the water problems. I'm going to make a part 2 to this video and do example 92.2. If you want to watch it, you may. If you want to just jump in, there are 2 more examples. There's a 92.2 and a 92.3. If you want to just carry on and do them yourself, that's fine. But I will make a separate video of me doing 92.2. Thanks, guys.